Hi everyone. Today we're going to be looking at the alternating series. Alright, so what I want you to do is I want you to recall what we were looking at when we first started developing the sequences and series on this specific chapter. Alright, we were starting with sequences, and in that start with sequences, we had something similar to this specific sequence, and that then tells us, or we were then able to analyze, that this sequence was an alternating sequence, meaning it alternates between positive, negative, so on and so forth. Alright, so the big question for us now becomes, what happens to this series? So if I take all of the terms in this initial sequence and I start adding them together, what happens to this series? Does it converge or does it diverge? Right? That's the question that we have at hand. All right. Now, some of you might be saying, well, you know, we could possibly use a comparison, right? And one of those comparisons that we could possibly use is the harmonic series. Alright, so we know we have the harmonic series, and the harmonic series is just this 1 over n. Now, it looks very, very familiar, or it looks very, very similar to this series that I have displayed first. But again, the big question is, does it converge or does it diverge? Alright, so what I'm going to do here is I'm actually going to go over to GeoGebra and show you a more graphical representation so that we can come up with a conclusion. Alright, so please follow me along. Alright, so here we are on GeoGebra. Now, I went ahead and I created this applet on GeoGebra to show you what's happening with this series. Alright, so what I'm going to do here really quick is I'm going to start graphing this specific series. Now, this graphical interpretation is just an interpretation that I am giving. Alright, it's not an actual graphical representation of what is occurring in general. Alright, but what I want you to notice here, what we have here is this first term. So what I went ahead and I did was I said, okay, well, if we're going to graph the first term, in other words, n is equal to 1, I'm going to make sure I graph it with this just line segment. All right. Now, my next line segment, this one here, is the next term of the series added to the previous one. So if you notice, the second term is 1/2. All right, and then the previous term was 1, so 1 plus 1/2 gets us 1.5, and here's that graph of it. So every new graph just represents a new partial sum of this initial series. All right, so here we go, 3 terms in, or 3 partial sums in. Notice that 3 partial sums in, this bar here, or this line segment, represents 1 plus 1/2 plus 1/3, which is given by 1.83. That should be repeating, but again, it shows what we need. Now, I'm just going to keep on creating this graph, so on and so forth, and I just keep on seeing these partial sums take place. All right, now I didn't go out large enough. I just went out to a few values, just enough to get a good familiarization. All right, now what I want you to see is that as you start considering all of these partial sums then look like they're just increasing and increasing and increasing without ever really tapering off. Which then tells us that the harmonic series that we're observing here diverges. All right, because again, there is no convergent for some limit. Now, let's look at the value that I had given you all, or this series that I have given you all. All right, so what I'm going to do here is I'm going to make sure I have my, my parentheses here. So let's go shift, and let's go back in. There we are. So this is going to be -1. And then I'm going to raise that to some power here. Let's go back on that. There we go. To some power, and that power was x plus 1. And I'm just using x's. Even though I gave you n's, naturally it still should be around the same thing. Alright, so here we go. So just making sure my function is the one that I gave you all. There it is. And what I'm going to do now is I'm going to start producing some of these terms. All right, so here we are. So these are the first two terms. In other words, this is a partial sum of that alternating series. So the first term was just 1, then the second term was 1 minus 1/2, because again it's alternating. So 1 minus 1/2 gets us 1/2, and then we're going to add 1/3 to that to get us in here 0.83, and we're going to keep going. And notice how it's alternating. It goes up, down, up, down, up, down. But what I want you to notice is it kind of looks like it is converging onto some value, right? Because more and more this sum, and again these line segments are just partial sums, those partial sums are getting closer and closer and closer to some value. Now on here I went ahead and I displayed this convergence line, meaning that this alternating harmonic series does converge, and it must converge to some value that exists between 1 and 0.5. All right, so that's kind of interesting. All right, so we do have this alternating harmonic series, and this alternating harmonic series does converge, whereas the initial harmonic series does not converge. That one diverges. All right, so interesting fun fact, this alternating harmonic series actually converges to the natural log of 2. All right, natural log of 2 is approximately 0.68. So if I kept going more and more and more, this partial sum here would end up at about 0.68, and then it would just go along this line. All right, so here is how we want to develop this idea of alternate series. How do we know that an alternating series converges or diverges? All right, that's what we're going to be working on. So let's go back over to the whiteboard, that way we can write some stuff up. All right, here we are. So in this particular case, yeah, it's going to go ahead and it's going to diverge. Or, sorry, my apologies, it's going to converge. Okay, so now that we have this, let's go ahead and let's write up this alternating series test. That way we can see how we're going to be working with it, and we'll go through a slight explanation of why it works and how it's working. All right, so here's your alternating series test. And this alternating series test says that if the alternating series given by the function -1 raised to the power of n minus 1 multiplied by b sub n, as n is equal to 1 and then tends to infinity, then the sequence or the series is explicitly given by b1 minus b2 plus b3 minus b4 plus b5 minus b6, and it just keeps going on like that forever. And then this says where b sub n, in other words that explicit formula, is going to be greater than 0, as long as it satisfies these two conditions. Number one, that it has to be non-increasing. So all of the individual terms that we're going to be identifying here for this explicit formula for b sub n's, they all must be non-increasing. All right, that does not mean that it's going to be increasing, it just means that it's non-increasing. All right, so number two, we're also going to consider that the limit of that function b sub n is also equal to 0, meaning that it tends to 0 as n goes towards infinity. If that's the case, then this series is going to be convergent. So anytime that you see some sort of alternating series, this is one of the tests that you want to go to automatically. Either this one, or you want to go over to the test for divergence to see what's taking place, right? Is it going to converge or is it going to diverge? Now, looking at this figure here, we could then see, okay, well, if we're looking at our first term, we said it was going to be greater than 0. So if we're going to be looking at our first term, well, the first term is going to give us our first partial sum. Then the second one is going to subtract out a certain amount, and that's going to give us a second partial sum. The third one is going to add a certain amount back into it, but not greater than the previous two, meaning it's going to give us our third partial sum, then our fourth partial sum, then our fifth, then our sixth, and we can just keep on repeating this over and over and over, and it gets us to this value of s, meaning that it does converge to some specific value. All right, so again, we might not be concerned with what value it is. All we want to know is, does it converge? All right, does it converge or does it diverge? Now, we're going to work on some examples to help us understand this a little bit more. All right, so here we go. We're going to work on these examples, and this is going to say test the series for convergence or divergence. All right, so we're going to work with part A. Part A is going to be this series given by 2/3 minus 2/5 plus 2/7 minus 2/9 plus 2/11 minus 2/13, and then this is just going to be repeating. All right, so we have this series that we're observing, and now we want to determine whether it converges or diverges. So the first thing that I'm going to do is I'm going to try to extract an explicit formula here. Right? We always want to make sure that we're looking at this formula. That way we can identify what it is or what kind of test that we want to be running here. All right, so the first thing that I'm going to do here is I'm going to say that this series that I'm looking at here has a formula, and I'm going to find that formula. Nice. All right, so let's copy that. Let's move this down here. Let's paste it. Look at that. Looking real nice. All right, make this blue. There we go. Perfect. All right, and then this is going to equal, I have a summation. It's going towards infinity. I'm going to index this at n starting at 1. Notice all the numerators are 2, and it's also alternating. All right, so that's one of the first things that I want to identify, is that this series is alternating. Alternating. All right, perfect. All right, so that's my first observation. And because it's alternating, what I'm going to do is I'm going to say this is -1 to the power of some n plus 1. Now, again, you can go ahead and you can say, okay, well, if the first term starts with negative, then we go to the exponent and just knock this one out, and then we just have -1 to the power of n. If it starts with a positive, then that means n beginning at 1, this index here must start at some n plus 1 value. All right, so now that we have this, let me see my numerator. My numerator doesn't ever change, so I'm going to keep my numerator the same as a 2, and my denominator does change. My denominator looks like it's all odd numbers. It goes from 3 to 5 to 7 to 9, 11, 13. So I'm going to denote this as an odd number, and all odd numbers can always be denoted as 2n plus 1 as long as n is an integer. And n being an integer, that still satisfies this whole summation, which means, hey, we're on the right track. All right, so there we are. So this is what we're observing to begin with, is this specific function. All right, so I have an alternating series, so what I'm going to do is I'm going to start using this alternating series test. I'm going to make sure to say, hey, this is going to be non-increasing. All right, so that's going to be my first thing. Number 2, I'm going to check that the limit for that explicit function tends to 0. All right, so let's go ahead and let's do that. I'm going to extract my b sub n. So my b sub n here is going to be 2 over 2n plus 1. All right, so let's go through, and I'm actually going to label this as f of n, simply because I want to make sure that it's non-increasing, and I'm going to use calculus to do that. All right, so here we go. Using that f sub n. All right, so I'm just going to really quickly rewrite f sub n to be a little bit more easier on the calculus mind. There we are. So that when I take this derivative here, f prime of n, all right, drop the exponent forward, that's going to be -2. Rewrite the function, subtract 1 from the exponent, there we are, multiply by chain rule, and that's going to be 2, which means my partial derivative here, sorry, I said partial derivative, I meant my derivative here is going to be negative 4 divided by 2n plus 1 squared. There we are. All right, looks pretty good. All right, now notice that n plus 1 is equal to 1/2, but 1/2 is not in the initial domain. So n cannot be equal to 1/2 in this particular case, right? It's not one of our points, it's this asymptote that we're initially looking at. Anything greater than that will always be negative or will always be decreasing because of this negative value. The denominator is always going to be positive, but then the numerator is always negative. Negative divided by any positive number is always negative, which means that my derivative tells me that I'm decreasing as n gets large. So, using the first derivative test, oops, I meant f of n. Cheetos. There we go. F of n, or in other words, b sub n, is decreasing as n goes towards infinity. Now, that's kind of nice because, again, we're looking for this to be decreasing, and that's going to be really good. Decreasing in our sense implies that this is non-increasing. Remember, all we want it to be is non-increasing. All right, so the fact that we got decreasing, that's actually perfect for us. So awesome. So we got this to be non-increasing, which is really good. So non-increasing. Awesome. That's what that gave us. All right, awesome. That's great. Now I'm going to check the limit. So now let's go ahead and let's check the limit as n tends to infinity for b sub n. So that's going to be the limit as n tends to infinity for 2 divided by 2n plus 1. Now this is a pretty straightforward limit. All I'm going to do is take the limit here directly. N is going to get very, very large. So that means the denominator gets large. That means the overall fraction goes to 0. So we actually met the 2 requirements. The 2 requirements for this alternating series test says that as long as we have our terms being non-increasing, and as long as the limit as n tends to infinity for the b sub n function is equal to 0, then the series is going to be convergent. So let's summarize. By the alternating series test, this series that I'm observing, which was n is equal to 1, negative 1 to the power of n plus 1, and that's 2 divided by 2n plus 1, is convergent. There we are. So this series converges, and again, what I'm looking for is, can you go through an argument providing calculus arguments to tell me that this is non-increasing? Secondly, can you show me the limit? And then third, tell me what series test you used. All right, so as soon as I'm able to see all that, awesome, and then you're going to summarize, tell me, okay, by the alternating series test or by some other test, comparison, limit comparison, divergence, whatever it may be, you can then tell me, hey, this series either converges or it diverges. That is my result. All right, so that's part 1, part A. Let's look at part B. So for part B, we're going to have this series where n is equal to 1, beginning at negative 1, going to n, and then this is going to be the square root of n divided by 2n plus 3. All right, so again, we have to test this series. So the first thing that I want to notice is that this is an alternating series. All right, simply because we have this negative 1 raised to some exponent, and that exponent is the index that will change. So that's going to provide me with an alternating series. chances are I want to go to an alternating series test. All right, so what I'm going to do for this is I'm going to interpret that alternating series as my b sub n. So I'm going to extract what is this b sub n function. That b sub n function is square root of n divided by 2n plus 3. Consequently, I'm going to call this my f sub n function. Now, the first thing that I'm going to do is I'm going to check that this is non-increasing. All right, so check to see that it's non-increasing. That means I'm going to go back to calculus and I'm going to use my first derivative test to determine whether this is going to be increasing or decreasing. If I find that it's increasing, well, then that's bad for business. But if I find that it's decreasing, then that's good for business. So let's go ahead and let's find that out. All right, so f sub n, f of n is equal to, I'm going to say this, n to the power of 1/2 divided by 2n plus 3, and let's go ahead and take that derivative. All right, in order to take this derivative, we're going to need the quotient rule. All right, so taking the quotient rule here, derivative of the top, that's going to be negative 1/2 n to the power of negative 1/2 multiplied by the bottom function, which is 2n plus 3, minus the bottom function, 2n plus, minus the derivative of the bottom, which is just 2, multiplied by the top function, which is n to the power of 1/2, all divided by the bottom denominator squared. There we are. All right, looking pretty good so far. So what I'm going to do right now is I'm going to factor some items out here just to make things go a little bit easier. So let's see, I have a half and I have a 2 there. Chances are I want to factor out a negative 1/2. Yeah, that looks about right. So we can factor out a negative 1/2 n to the power of negative 1/2 and see what that leaves us with. So I'm going to factor this from the numerator. So negative 1/2 n to the power of negative 1/2, that's this whole term, so that only leaves me for the first term of 2n plus 3. The second term, I took out a negative, so that now becomes a positive. Now from this 2, I'm taking out 1/2, which means I'm going to be left with 4, right? Because once I multiply this negative 1/2 in, negative 1/2 times 4 should get me negative 2. And then n, I believe I have n to the power of 1 left over. Because if this is n to the power of 1, then when we redistribute n times n here, the exponents are going to add. So negative 1/2 plus 1 should get me 1/2. And then I have my denominator of 2n plus 3 squared. All right, let's clean this up just a little bit more. All right, I'm going to leave the negative right out in front, and everything else is going to go to the denominator here. So I'm going to go ahead and combine these like terms in these brackets. That's going to be 6n. So that's 6n plus 3 for my numerator. Remember, I'm leaving the negative out here, the negative there. So that 2 comes down, so that's 2, and that's going to be square root of n down here, multiplied by 2n plus 3 squared. There we are. So there's my derivative. Whew. Fun times, right? Oh my goodness. Okay, so now let's find these critical values that we need in order to start conducting this first derivative test. All right, so, whoops, let's actually redo that. There we go. All right, so let's look at what we have. We can have n is equal to 0, so that's going to be one of the values that I'm looking at. The next value, I'm going to set this numerator equal to 0. So subtract 3, divide by 6. All right, that should be 1/2. So that's going to be negative 1/2. So I'll put negative 1/2 over here. All right, let's look for the denominator. The denominator here, this is going to be 2n plus 3, so that's going to be negative 3/2. So I'll put negative 3/2 somewhere in here. There we are. Now let's look at the initial domain of this initial function. So my initial domain here, well, n must be greater than 0. So n must be greater than or equal to 0, and we also have that n cannot be equal to negative 3/2. Okay, so there we are. All right, we have those few things that we need to observe. Oops, I am so sorry. Did I put negative 3/2? Oh, Jesus. I have no idea why I did that, everyone. My apologies. Negative 3/2 is actually over here. There we are. So that's negative 3/2. So again, what we're looking at here is to be increasing, or in other words, non-decreasing. But for the values that we're looking at, our series begins at n is equal to 1. N is equal to 1 actually begins somewhere over here. That's n is equal to 1. All of these values over here are the ones that are increasing or decreasing, so we don't really have to worry about that, right? So all we know is that because this is going to be negative, as we start picking any value in here, any value will, that's going to work here, it's going to work here, and that's always going to be positive. So positive, positive, and then this is going to be positive, but then it's going to be multiplied by negative. Therefore, that's always going to be decreasing. So b sub n is decreasing by the first derivative test. Nice. All right, so we got that it's decreasing. Now let's go ahead and let's check limit-wise. What is happening limit-wise? I hope that we can get that the limit is equal to 0, because if we can get that the limit is equal to 0, then awesome, we're going to be convergent. So let's go ahead and let's check it out. Let's check out the limit as n tends to infinity for my b sub n, and that was going to be the square root of n divided by 2n plus 3. All right, here we go. Now, according to Calc 1 process, I can go ahead and I can multiply both numerator and denominator by the largest power in the denominator, which is n. So in this particular case, I will wind up with limit as n tends to infinity, and this here is going to be 1 over the square root of n divided by 2 plus 3 over n. And as we send n off to infinity, numerator goes to 0, this piece goes to 0, so that's going to leave us 0 divided by 2, and 0 divided by 2 is, lo and behold, 0. So, what do we now know about this series? Well, what we know now about that series is that it's going to converge. So let's go ahead and let's write it up. Let's say so. Let's put the series in here. There we are. And let's make that blue so that it jives with everything. There we are. And let's move it over. There we are. So the series here is convergent and I'm going to say by the use of the alternating or the alternating series test. There we are. Awesome. So this series does converge. And again, the hardest part here was to show that it was going to be non-increasing, which means for us, we wanted to make sure we get to that decreasing portion. All right. So that was the example for part B. All right. Not too bad. All right. Not too bad. Now, let's go through and let's check another example. Let's go with part C. All right, for part C, I'm going to be looking at this series here, -1 raised to the power of n minus 1, and this is going to be for arc tangent of n. All right, awesome. So, let's go ahead and let's identify my b sub n. All right, the first thing I identify here is that this is an alternating series, which means I could possibly use my alternating series test. All right, so that's going to be kind of nice. So let's look at my alternating series test. All right, so that's going to be b sub n is going to be arctangent of n. All right, so I'm going to be looking at arctangent of n. Now, I'm actually going to use GeoGebra for this to elaborate a little bit more. All right, so let's go off to GeoGebra. All right, here we are on GeoGebra, and what I'm going to do here is I'm just going to insert arctangent. Oops. Arctangent, let's keep going. There it is. Arctangent of x. There we are. All right, so as we start looking at arctangent of x, in other words, just tan inverse, what I'm going to do is I'm going to actually go to the second portion, or that second part of the alternating series test, which says that as we go towards infinity, the limit of this function must be equal to 0. Now, is that the case in this particular function? No. The reason for that is because this function has an asymptote, or it has two different asymptotes. It has these two different asymptotes, one being at pi halves and the other one being at negative pi halves. All right, so we're then able to say, well, as this tends to infinity, this is not going to equal to 0, which means by the alternating series test, we don't know what it is. All right, so the alternating series test only tests for convergence. It does not tell you whether it diverges or not. If you don't meet the two requirements, you cannot say that it diverges. All right, so let's go back to the drawing board and we'll see what's going on. All right, so here we are. So again, as we start looking at the limits as n tends to infinity for arctangent of n, this is going to equal to pi halves. All right, and again, this tells us that we cannot use the alternating series test. I hope you're all okay with me abbreviating. A for alternating, S for series, T for test, so AST. So cannot use AST, alternate series test, because again, this does not equal to 0. All right. And I'm just going to say here, because the limit as n tends to infinity for b sub n is not 0. All right, so we kind of have our hands tied. All right, now let's go through and we're going to say, okay, well, you know what? Mr. Castro didn't really give us this for the specific reason that we're going to have our hands tied, right? There must be a way around this. All right, and indeed there is a way around this. The alternating series test tests for convergence. Well, we're not convinced that this converges. All right, the function might converge, but the series, right, we have no idea. So let's go ahead and let's instinctively try to identify a different test to see if this converges or diverges. All right, so what I'm going to do here is I'm going to say, okay, we have a hint that it might not converge. All right, it might not. We don't know that yet. All right, so what I'm going to say here is I'm going to say let's instead use the test for divergence. Now, the test for divergence, we actually covered that back in, I believe it was the second section in chapter 11 when we were talking about series. All right, I'll put a card up here in the right-hand corner to link you to that video. So we're going to use that test for divergence. The test for divergence says that if the limit as n tends to infinity for the function that we're looking at does not exist, or if it's not equal to 0, then the series is divergent. All right, so what I'm going to do here for this test for divergence is I'm going to assume my function, that explicit function, I'm going to call this a sub n, is this negative 1 to the power of n minus 1, and this is going to be arctan of n. So now what I'm going to do is I'm going to identify this limit here. All right, let's go with the limit as n tends to infinity for this function, which is negative 1 to the power of n minus 1 multiplied by arctan of n. Now, remember arctan. Arctan, as n tends to infinity, we get pi halves. But as n tends to negative infinity, then it's going to be negative pi halves. All right, so that means if I multiply arctan by negative, I'm just going to be tending towards negative infinity, which will mean that I'm tending towards negative pi halves. So what's happening here is that my limit just keeps bouncing between pi halves, negative pi halves, pi halves, negative pi halves, pi halves, negative pi halves. In other words, does this limit exist? This limit does not exist for this function, negative 1 raised to the power of n minus 1 multiplied by arctangent of n. All right, now that's nice because the test for divergence says that if you can get this limit to not exist, then what happens to this series? Well, it diverges. All right, so that's really, really awesome. That's really good for us. Really good for business. All right, so let's go ahead and copy that. And I'm going to go down here and I'm going to say, so let's insert, there we are. And let's go ahead and make this blue. There we are, looking good. All right, let's move it here. There we go, not too bad. So that series is divergent by using the test for divergence. All right, so again, as you started analyzing, well, this is an alternating series. Maybe I can go to the alternating series test. Notice that the alternating series test, it gets you at an impasse because the limit is not 0. Well, doesn't mean that it diverges, but it kind of hints at, hey, you might want to use something else. So instead, we test for divergence and we use the overall function, not just the piece that's not alternating. We use the overall function. Using that overall function, we can then find the limit to say, well, if n gets very large, it's either going to be pi halves or it's going to be negative pi halves depending on this sign, which means it never actually gets to a certain limit. So this limit does not exist. And because that does not exist, this means that my series is going to be divergent by that divergence test. All right, awesome. All right, so I hope you all enjoyed this lesson, and I will see you all ready for the next one.